Thank you. While we're waiting for the slides, I'd like to begin by thanking you for having the opportunity to present here. We have a strong team, as has just been introduced, and it has been a real pleasure and privilege to work on this data set from the Cavoni laboratory.
Excuse me, you are the only one to present the whole...
I'm presenting everything.
Okay, you are welcome, yourself and your colleagues here. We will listen very carefully what you want to say to us. Thank you.
Okay, so yes, so I'm the speaker, but I have colleagues with a wide range of skills and complementary skills, and we've been working very hard to put this together. We think that Italy is ahead of most of the world in taking on this problem of trying to quantitatively assess seismic hazards and associated with production. So we're glad to be here. Interesting. The outline is that I'll be giving a very much physics-based approach to the problem. We'll be looking at fault loading, fault strength, and pressure changes. Fault loading occurs by stress changes. Fault strength can change both from changing the normal stress and changing the pore pressure. It's very interesting. I'll be talking about Coulomb failure and Coulomb stress changes. We'll see if this problem extends through the rest of my talk. At least the first slide looked okay. And talking about tectonics and earthquakes, structurals, and historical seismicity, and also talking about pressure changes from production and injection, and estimates of flow parameters from field tests. The main piece of this talk is going to be the presentation of the results of coupled flow and geomechanical models of changes in stress. We've developed a new two-way coupled flow geomechanics models that includes faults, and we are going to use this on the Cavoni field as an illustration of how quantitative calculations, physics-based calculations of change in stress and strength on faults can be put into a reservoir context. And finally, the approach that we've developed we think has very useful implications for balancing risk and production. So I'll begin here with a very conceptual view of the earthquake cycle. What's shown on this plot is the shear stress on a fault plotted as a function of time. From loading of the fault, the shear stress increases, and then when it reaches the strength of the fault, it decreases, releasing seismic energy, and so forth. We wish the Earth were this simple. Unfortunately, the Earth is not this simple, and we have both the strength of faults varying with time, perhaps as pore pressure intrudes a fault, or the normal stresses clamping a fault shut are released, and also the loading rate can increase as a function of time. Sometimes it will be loaded faster, other times it will be loaded slower. So we don't know how to predict the exact time that an earthquake will happen, but we can predict when earthquakes are more likely by looking at how the strength of the fault is balanced against the shear stress on the fault. So the way we talk about this is in terms of a quantity called the Coulomb stress, and we imagine that we have slip on faults when this Coulomb stress reaches a critical value. On the left side of this equation, we have the shear stress, which is caused by loading of the fault. And on the right side of the equation, we have the strength of the fault. So there are parameters that control the strength of the fault are the coefficient of friction. We heard about that earlier this morning. The normal stress acting on the fault. If you put more normal stress on the fault, you make it stronger. And finally, the pore fluid pressure. If you increase pore fluid pressure, you weaken the fault. So we talk about a quantity called the Coulomb failure function, or the Coulomb stress change, delta tau C, and that's just taking the right-hand side of the equation and subtracting it from the left-hand side of the equation. So basically, we quantify the approach of loading to the strength of the field. Of course, we can't predict times of earthquakes, but we can predict earthquake likelihoods. So the way we do this is to look at the way a system of faults might respond to a stress change. So this is a rather complicated diagram. On the top row, I'm making plots of the shear stress accumulation on a fault system as a function of time. And on the bottom row, I'm showing the rate of earthquake activity as a function of time. So as a reference case, let's assume that the stress in this system is increasing at, say, 0.1 bar per year. That's the loading rate. We will have some background rate of seismicity. And then at some time, the rate of stressing increases. It takes the Earth a while to catch up, but once it does, the rate of earthquake occurrence will increase. And the larger the stressing rate increase, the larger will be the increase in the rate of seismic activity. In the right column, we see what happens if we're moving a system along, increasing the stress, and then impose a sudden change in stress like we would have if we had an earthquake, and then continue to increase the stress at the background rate. Well, what happens is we see the familiar aftershock sequence, aftershock decay, where we have immediately after the earthquake, we have a great increase in the rate of activity, and then that activity dies over time. Its approach to the background rate depends on what the loading rate is. If we have low loading rate, it takes a long time to approach the background. If we have a rapid loading rate, it takes a short time to approach the background. Okay, so we've been looking at the Emilia-Romagna sequence, and this sequence illustrates these concepts extremely well. So in May, on the 19th of May, there was a magnitude 4 foreshock, very close to the hypocenter, as close as we can't really tell the difference in location to the hypocenter, and that increased this Coulomb stress in the region of the eventual hypocenter. This is the plot showing the change in Coulomb stress. What you need to remember is that red values mean that the fault is more likely to fail. Blue values mean that the fault is less likely to fail. So, for example, the plot pins here at a half a bar, and within the region where the color scale is saturated, the stresses reach up to 30 bars. Anywhere where you can see the orange colors are places where stress is larger than 0.1 bar or 0.01 megapascal, which has previously been mentioned as the critical stress for triggering earthquakes. So it is not at all a surprise that the May 19th earthquake triggered the May 20th earthquake. We might ask, what were the Coulomb stress changes caused by the operation of the Cavoni field? I'll talk about those in more detail later, but this is a plot showing the change in Coulomb stress in the area of the hypocenter of the May 20th event. Now the color scale is in millibars, okay? Not bars, but millibars. And so the changes in Coulomb stress on this eventual fault plane from the effects of production at Cavoni is on the order of 1 or 2 millibars. Okay? So as geophysicists, sometimes we have difficulty understanding concepts of units and bars and megapascals and so forth. So looking for an illustration of how large 2 millibars really is, and wondering what the weather would be like today in Rome, yesterday I looked at the map, the weather map of pressures, okay? And so pressure variations here are contoured with a 4 millibar contour interval. The pressure here was about 1,012 millibars. In England, it was 988, and in Russia, it was 1,028. So variations in pressure much larger than we would see from production at Cavoni at the hypocenter location. And today, I checked this again, and the pressure here has dropped by 4 millibars. So the change in stress on the Earth, the variation in stress on the Earth from yesterday to today is about the size of the variation in stress caused by 30 years of production at Cavoni at the hypocenter of the, so that's just to give you a calibration. Okay, when the May 20th event happened though, it actually made very strong perturbations to the state of stress. Here's a very nice result by Pezzo et al. Showing the stress changes on the fault plane of the May 29th earthquake caused by the displacement from the May 20th earthquake. And the changes here are up around 6 bars, so they're quite large. So Basically, the Emilia-Romagna earthquake sequence, which what I have plotted here is the daily number of earthquakes as a function of time. This is the May 19th foreshock. This is the May 20th main shock. Activity jumped up, died back down. The May 29th aftershock happened. Activity jumped up and died down. Similar. And so this system behaves exactly as we expect it to behave from our understandings of Coulomb stress changes in tectonic environments. So we're fairly confident that we have some idea. We have a calculation that can reproduce results. Okay, but the question that was left pending by the Ikesi report is what can you say quantitatively about these kinds of things? So we, ASO Mineraria, asked our group to develop a model to address this question quantitatively at the reservoir scale, put together the Cavoni laboratory. And so what I'm going to do now is illustrate the geomechanical model that we put together. So we need to start with a model of the geologic structure. This is the area that should now be familiar to us, the area of the Cavoni field, which is shown here in green. This is the epicenter of the 1570 Ferrara earthquake. This is the magnitude 6 May 20th event. This is the aftershock event that happened near the edge of the Cavoni field. So we start with a geologic representation of the structures. These geologic models were put together with great effort by the group at Harvard, starting with seismic sections through the area and ending up with geologic representations, geologic structural models that we then put into our model. So on the right, you see the seismic constraints. On the left, you see a typical cross-section through the Cavoni field. This Mirandola fault is the fault that the May 29th earthquake, the aftershock, happened on. So that's some information from geology that we incorporate. We also have information from seismology that we are going to incorporate, and the illustration here is showing how earthquakes vary as a function of place, as a function of space, and of time. In this map, the white dots show earthquakes that happened before the sequence. The red dots show earthquakes that happened, the aftershocks of that sequence, and the green dots, which you can see a few of, are the more recent earthquakes. It's a mess. It's hard to see what's going on here, but it's useful to draw a line from east to west here, centered on the Cavoni field at the injector well, Cavoni 14, and then plot on time on the horizontal axis and distance on the vertical axis, either distance to the north or distance to the south. So the total range of distance here is 40 kilometers, plus or minus 40 kilometers. So this is the region of the field. And what we see is that earthquake activity happened outside the field over time. Once the May 20th earthquake happened, activity occurred within the field. But prior, starting in 1964, there was very little seismicity that could be located by the ISC in this area. So I'll come back to this plot later on when I discuss the geomechanical model to use this information as a test of the geomechanical model. We also have constraints from GPS. We can compare, there's a very nice study by Devati et al. Looking at the variations in velocity perpendicular to the structure here over time. The scale here is in millimeters, 0, 1, 2, 3. The distance here is in kilometers. And the bottom line here is that over a distance of about 50 kilometers, there is about a millimeter a year convergence across all these structures. That corresponds to a strain rate of 0.02 microstrains per year. We can translate that into a stressing rate, which we can use then in calibrating our stress accumulation models by multiplying it by Young's modulus. That gives us a stressing rate of about 0.02 bars per year, okay, or 20 millibars per year. Across three faults, there's an average rate of about 0.3 millimeters a year. The rate of 0.3 millimeters a year from geodesy corresponds well to the same estimates of the rate of deformation from geology. So we have agreement on geologic timescales of, say, 500,000 years and geodetic timescales of 10 years that the strain accumulation is basically going on at the same rate. There's no recent acceleration or deceleration in strain rate. Okay, so we think that we have a pretty good constraint on what this background stressing rate is, and it's 0.02 bars per year. All right, so now to move from tectonics to reservoirs, we need to include the effects of fluid flow, pore fluid flow. And just a few words here about the basics of pore pressure diffusion. The change in pressure with time is related to the diffusivity times the second derivative of the pressure field plus a flux term. And if you put in the equations for Darcy flow, you end up with 5 parameters in this equation. Okay. Some of these equations we know quite well. We have very good records of what the fluxes are. We know what the viscosity of the fluid is. We can estimate well the compressibility of the formation in the fluid. But we don't have very good handles on the permeability or the porosity, because these can vary over reasonable time scales, distance scales. And so we can't interrogate those directly. And so what we need is something like a test, like the injection test carried out by the Cavoni laboratory. So what this is a plot showing the pressure as a function of time for one of the tests in the Cavoni well. And in this case, the injection flux was varied on time scales from minutes to weeks. And the pressure response can be varied, can be observed on time scales of days, minutes to weeks. And so there can be a fit obtained to fit the model predictions to the observations to obtain these parameters in the vicinity of the well. We can move further away by making use of the fact that we have observations or records of the daily water injection starting in, well, here in 1999, the field began in the early 80s, up until the present. It's hard to see what's going on here in this plot, so I've just compiled those into monthly water injections. So you can see the injection rate increased, relatively reached a steady state, and then it decreased. And accompanying that is a kind of gradual increase in injection pressure, followed by a decrease in injection pressure when the flux, the flow in and out of the reservoir was varied. Okay, so we have time constraints on the flow parameters on time scales from minutes to decades, and it turns out that those two estimates are remarkably consistent. One other thing I'd like to say about fluid flow is two important things. One is that when we have sources and sinks, so we have producers and injectors nearby, once we get a little further away than the distance between those two, the effects add, they cancel. Okay? So in Cavoni, the net effect has been reduction of pore fluid pressure over the decades that the field has been operating. So we need to include both the production and the injection in our calculations. Diffusion is rapid over short distances. It's slow over long distances. We can define a distance over which pressure will diffuse over some characteristic time scale. And the parameter that governs that is this diffusivity that we get from the Cavoni lab test. And basically, pressure pulses diffuse around 100 meters in a day. They go maybe 400 meters in a week, 3 kilometers in a year, and in 100 years, they will only go 30 kilometers. Okay, the hypocenter of the May 20th event is about 30 kilometers away from the Cavoni field, so the information that Cavoni activity has been going on has not yet reached the hypocenter of the 2012 event. Okay, so that's some general considerations of fluid flow. Now we need to couple these two things together. We need to couple fluid flow and geomechanics. So we have one set of equations, I just showed you those, that govern the mass conservation of fluid. And we have another set of equations that govern the stress, strain, and displacements in the earth. So they need to be coupled. There's a coupling between the flow and the mechanics, which is important because, as we know, when we increase the pore fluid pressure, we decrease the effective stress. Okay, so there's a direct coupling between flow and mechanics. But there's also a back coupling. When we change the stress, we change the volume. When we change the volume, we change all of the reservoir properties like the porosity and the permeability. Okay, so it's very good to have a model that can handle both flow and geomechanics at the same time. And one of the great recent developments is that Ruben Juanes and his group at MIT have developed a coupled fluid flow and geomechanics simulator. This runs on a finite element grid for the geomechanics. It runs on a finite volume grid for the multi-phase flow reservoir. These two grids are congruent, that is, the finite volumes match exactly the finite elements. It includes a sophisticated formulation for fault, deformation, and slip, which allows faults to slip on discontinuity surfaces. It's fast, parallel, modular. You can use either hexahedral or tetrahedral grids and include interesting rheologies like viscoelastic and elastoplastic rheology, realistic friction parameters on faults. So this provided a great opportunity for our group to extend our previous work and actually build a detailed physical-based model of what's happening in the Cavoni field. Okay, so moving on to that model, this is showing basically the domain that we carved out of the Earth to model. Numerical models have to assume a finite domain. We assumed the domain, which is about 30 kilometers along strike, about 25 kilometers across strike, and 20 kilometers deep. This is a contour map showing the anticline, which forms the Cavoni field. These dots, the blue dots are producers, or green dots I guess they are producers. The purple dot is the Cavoni 14 injector. And we have this field pretty much centered in the center of our mesh. And this model also includes the Mirandola fault. So what we're going to do is take this model and we're going to evaluate the pressure and stress changes that have occurred over the 33 years that the Cavoni field has been operating. So here on the left, you can see a structural representation of this. The reservoir is this anticlinal shape. The surface is up here where the wells are. These wells are connected down to the crest of the anticline, where most of them are producing. One of them is injecting. And this surface, which we will look at many times, several times during the rest of the presentation, is this Mirandola fault surface. So this is a plane representing the Mirandola fault extending down to depths of about 20 kilometers. Okay. On the right side, we see a 3D perspective of the mesh. So you can see between the yellow lines here, the reservoir, where the fluid is injected and produced. And you can see that the Mirandola fault divides the footwall from the hanging wall. Okay, so this is the structure, and we put in a realistic geometric curvature of the fault. Okay, so going to move on to the results, and I'm going to take a few minutes to explain what we're looking at here. So in the upper left corner here is a cross-section through this domain showing the pressure variations at the end of the simulation, so in year 2013, cut through a section which is very close to the injector well near the center of the field. So the reservoir is this region just below the brown region. And you can see that near the crest of the reservoir, the pressure is high. That's what the red color means, because of the local injection. Down here along the fault, in this particular location, the pressure is low, and that's because this area has been affected by the greater production than injection. So overall, we have a net production here. The frame on the right here gives a model, shows the pressure in the reservoir with a lot of vertical exaggeration. So we're looking at a three-dimensional model. And the important thing here is that this red spot is at the location in the anticline of the Cavoni 14 injector. Okay? And so the scale here, we're going from 70 bars of excess pressure to 30 bars at the lowest here of depletion, pressure reduction due to the production. And then finally, the bottom plot, which we will see several times in the slides following, is a projection onto the Mirandola fault. Well, not a projection, but it's a rectangular representation of the pressure variations on the Mirandola fault. So we have high pressure at the crest of the anticline. That pressure decreases by the time we get down to the Mirandola fault. So these are not the pressures at the injection site, but rather these are the pressures by the time the flow is communicated to the fault. Okay, and in this location, so this is the depth scale going down to 20 kilometers. This red dot is the region on the fault plane which is closest to the injection well. It has high fluid pressure because of the injection. And everywhere else on the fault, the pressure is low because this area has been produced. So we have net pressure reduction here. Okay. So this is one view of what we're seeing. This is the pressure field that has been calculated using the flow model. The other quantity which is of interest is the change in Coulomb stress, the net effect of whether we are actually promoting or failure or reducing the probability of failure. So this is a complicated plot. I'll walk through it slowly. We're now, again, looking at the Mirandola fault. On the left panel, we're seeing the shear stresses exerted on the Mirandola fault by the operation of the reservoir. Okay? And these are contoured. The maximum color scale here is plus or minus half a bar. This is the area closest to the injection well. Okay? And in the areas of production, the compaction of the reservoir is trying to drive sense in a normal fault motion. So that above the reservoir, it's trying to cause subsidence, and that reduces the shear stress driving thrust faulting. Except in the area of the injector, where the increase in pressure tends to promote thrust faulting. And so the other thing that happens is, similar thing below, the pressurization tends to reduce the effect of thrust faulting below, and the effect of production increases the shear stresses. So this is the shear stresses. We can also look at the normal stresses. And so basically what's happening with the normal stresses is that as a result of this depressurization, because the reservoir is contracting, we're pulling the hanging wall away from the footwall, which tends to reduce the fault strength, tends to promote failure. Okay? So the effect of production here is to destabilize the reservoir. The effect of injection is to stabilize the reservoir. Okay? And then we put all these together, and what we see is the net effect, including the effects of shear stresses and normal stresses. And essentially what we're seeing is that, in general, we stabilize the region above the fault. There's some destabilization below the fault, except near the injector, where we are causing more stabilization beneath the injector. Okay, so that's what comes out of the model. Again, the stress magnitude here is maximum of half a bar, and the spatial scales that we're seeing this occurring on are 1 or 2 kilometers, below which we're seeing very little change. Okay, so what I'm now going to do is show you a movie showing variation in pore pressure on the left side, variation in Coulomb stress on the right side, as a function of time, starting in 1980 and running through 2013. Okay? And these, again, both of these will be projected onto this Mirandola fault. So these are the stresses acting on the Mirandola fault. You can see the Coulomb stress change happening relatively quickly. Now we're up to the early 90s, and injection is beginning, so that's beginning to modify that effect. We have continued growth of the, and then eventual decay of the stresses after production was shut down following the earthquakes. Okay, so we can make a movie. We can see how stress changes with time. We can see the counterbalancing effects of production and injection. And we can also see the spatial scale over which those two effects cancel each other out. I'll run this one more time just to show you what's going on here. Again, production is destabilizing. We're beginning injection here. It's beginning to stabilize. As expected, over time scales of decades, the pressures are not diffusing very far through the system. And we have this cancellation over short spatial distances of pressure increases and pressure decreases. Okay, so this is the basic result of the geomechanical model. All right, so coming back, how does this relate to the seismic history? This is the same plot I showed you before. This box in here now is the region that we just modeled. And again, we're looking at earthquake activity from 1965 to 2012. The tick mark here is plus or minus 5 kilometers. That's about the size of the area that was influenced by the changes in stress from production and injection. And what we see is during this time, nothing happened until this, the main shock from 25 kilometers away, its effect, it generated the aftershock and so forth. Okay, so there seems to be an absence of activity in this area where our model seems to suggest that we might expect an absence of activity. We can't be definitive about that result because these are ISC locations and we don't know how, well, the accuracy of these is larger than the size of the symbol. Okay, so I do not know that these earthquakes did not happen in the Cavoni field, but and something like that would require, of course, better earthquake locations, which I think is part of what we've heard is going to happen. Another thing that we get from this model, which we can use to calibrate the model, is that we get surface deformation. And if we can observe the surface deformation, we can use it, again, to constrain the parameters in our model. For this particular case, the Cavoni field, because the injection and the production were so well balanced, the surface deformation that results is very, very small. We are showing here the three-dimensional surface deformation. What's contoured is the east-west displacement on the left, the north-south displacement on the south, and the vertical displacement, sorry, in the middle, vertical displacement in the center. What we see is a predicted subsidence over this 3 decades of 4 millimeters. Okay, so 1 millimeter a decade is beyond the ability of geodesy to detect, but there are other places where if we have larger pressure variations or less equally balanced production and injection, where we can end up having surface deformation being an important thing to look at. Okay, well, since I'm standing between everybody and lunch, I'll quickly wrap up here with the summary.
Thank you.
So again, seismicity is determined by the interplay between fault stress, loading, and fault strength, also loading or pore pressure. In Italy, tectonic stressing rate is high. It's a big problem. We need to compare the stress from production and injection to that tectonic stress rate. Changes in pore fluid pressure change fault strength. Changes in normal stress, which result from this poroelastic effect, change fault strength. And changing in shear stress, again from the poroelastic effect, changes the loading on faults. And this can both stabilize and destabilize faults, depending on which way the system is working. We've used geomechanics and flow models to evaluate this stress from production. I think this is the first time that this has been done with a two-way coupled flow geomechanics model. We drive this by the actual production and injection, and it matches well the observed well pressures. We don't have good enough observations of surface deformation for that to be a test. The surprising result, I did not expect this going into this, is that the injection mostly stabilizes the Mirandola fault. Okay? And that's because the effects are to clamp it shut. Okay? So the normal stress effects dominate, excuse me. There is a region of destabilization from the production because production is unclamping the faults. But those regions are relatively small. They're on the order of a couple kilometers in dimension, and they're fairly shallow. The changes in Coulomb stress are much less than the tectonic stresses outside the immediate vicinity of the reservoir. So we can determine where we need to confine our observation to make it have an impact. It agrees with historical seismicity pattern or does not disagree with it. And finally, we have this new tool to forecast and mitigate seismicity associated with production activities. And we hope that this can be applied elsewhere and by others. So, thank you.
Thank you very much. It was a very nice and interesting presentation. I think that more or less we are on time, so we are now ready for the